Hi, I'm James Amano. I am the Senior Director of International Standards at EHS at SEMI headquarters in Milpitas, California. And today I will be talking about next generation standards for security, equipment data acquisition, and back-end data management. Okay, so we only have a few minutes today, so I will jump right into it and start with the next generation of equipment data acquisition standards. Now, shorthand, we call these EDA standards. Just keep in mind that this is the semi-EDA, right? Equipment data acquisition. You'll also hear these referred to as the interface A standards, especially for those of you that were around in the Semitech days. So what's really driving all this? Well, smaller feature sizes and more restrictive tolerance have really intensified the need for greater visibility into our entire manufacturing process. And our current day fabs really need to gather and evaluate constant streams of data from hundreds, if not thousands of sensors in greater amounts than ever before. So why do we do this? It enables real-time optimization of manufacturing processes, improving our yield and mitigating abnormalities, and this thereby enhances productivity by reducing cost and cycle time, which is really what it's all about. So the Semi-EDA suite is a collection of semi-standards, not just one standard. It is a collection of semi-standards that define high-speed data publication from any equipment to any data consumer through web services. And manufacturers are increasingly adopting this EDA suite to address their demand for big data applications that analyze real-time information reported by equipment. So like with all standards, the EDA suite evolves and is updated with the needs of the industry. And currently we are working on what's called Freeze 3. Now let me first define what we mean by freeze. So if you look on the left-hand side here, each freeze identifies the specific versions of all the different individual EDA standards that compose the suite. And these specific versions are used by both equipment suppliers and the IC makers as a unified set to implement the interface. And as I mentioned, these standards are continuously evolving. And the previous freezes were implemented in 2005 and 2010. Obviously, since 2010, technology has come quite a long way. So what are we doing in the new Freeze 3? So first off, integrating HTTP2 with gRPC and protocol buffers technology. Fundamental reasons for doing this here: improved performance and more efficient data transfers, better network security to protect the data that's being exchanged, and easy adoption with support of multiple platforms and multiple programming languages. And this will enable higher data volumes going through the fabs, facilitating big data analysis, allows us to detect and predict problems, make better decisions, and minimize equipment downtime. And I won't go into the details here, but if you are interested, this describes really at a granular level what's going on in this upgrade from EDA Freeze 2 to Freeze 3. Fundamentally, though, look at the bottom line here. Freeze 3, more data, faster. Okay, let's move on to fab and equipment information security. So as the increase in data, right, it's a good thing. We can optimize our manufacturing processes, share data across the fab. However, the converse of this is there's more security challenges. There's more vectors now for virus introduction, and this includes both equipment installation and remote access, software installation and services, and there's been a lot of visible outbreaks that have impacted tools and led to shutdowns across multiple fabs. So protecting IP within data is becoming more and more complicated as, again, we're sharing more data to enable fault detection and classification, predictive maintenance, automated. The good news is we have some major activities underway to address these challenges. The first is the Fab and Equipment Information Security Taskforce. This is driven out of Taiwan. And the group is developing standards to better address software end-of-service issues in order to prevent virus attacks. And especially here, we're looking at older equipment. And its counterpart is in North America, the Fab and Equipment Computer and Device Security Task Force. And this group, led by Intel, is working on standards to ensure computer and device security both inside and outside of the fab. This includes protecting computer systems from theft or damage to their hardware, software, or data, and also protects against misdirection of services. And a strong message here from TSMC encouraging the entire supply chain to work together within the program to establish these critical standards. Finally, I'll wrap up with what we have going on in the back end. So if you look at this comparison here, you can see the challenges, right? front end, we have a homogeneous material, standardized carriers, right, host interfaces, etc. And then you look at the challenges in the back end, lots of different materials, no standards, minimal host interface. So there's three activities I'd like to focus real quickly. First is RITDB, which is the next generation standard test data format. This enables real-time streaming and adaptive test. Tester event messaging for semiconductors, standardized method of communication between host and test cells, and traceability. So two things I want to focus on here. T23, this is the spec for single device traceability for the supply chain, and E142, which essentially enables tighter quality control requirements for advanced packaging and assembly. So that's a lot of information. I realize I've gone through this very quickly. Any questions, please contact me, jamano@semi.org, and thank you very much.
Good afternoon, ladies and gentlemen. My name is Kwakman. In this short talk, I would like to present to you how electron microscopy is used in state-of-the-art semiconductor manufacturing, why further automation is needed, and how semi-standards activities can play an essential role in enabling such automation developments. Control of high-volume manufacturing of semiconductors is achieved with inline metrology and defect inspection in combination with wafer-level electrical yield testing. But because device structures have become extremely small and complex, also transmission electron microscopy, or TEM, is used more and more for reference and calibration metrology, but also to do root cause analysis of defect and yield excursions. As you can see from the graph, the demand for high quality and efficient TEM analysis has exploded in recent years, which puts a lot of pressure on both microscopy suppliers and IC manufacturers. TEM microscopy requires a workflow with different tools. The workflow starts with the preparation of very thin TEM lamellas from full silicon device wafers with a focused ion beam system. These TEM lamellas are then extracted from the wafers and placed on the lamella carrier, and this lamella carrier is then transferred to a transmission electron microscope in which the TEM samples are analyzed. Today, lamella preparation and extraction from full wafers is automated, and also data acquisition and TEM metrology is automated. However, TEM sample transport between tools is still manual, with operators using tweezers to manipulate the very fragile lamella carriers. It's slow, prone to error, and not really fab compatible. So therefore, late 2017, a new initiative was started together with the Semi-Standards organization to enable developments of fully automated TEM workflow solutions that are open standard rather than proprietary and industry-wide accepted. A new task force was created, including IC manufacturers, microscopy suppliers, lamella carrier suppliers, and material and automation suppliers. The charter of this task force is to develop semi-standards for fully automated TEM lamella carrier transport that are necessary to guarantee full compatibility between the different TEM workflow tools from different equipment suppliers. For that, the two most relevant and urgent standards to be developed are a standard for the lamella carrier itself and for the lamella carrier container that allows the lamella transport between the different tools. When comparing TEM lamella carrier transport with silicon wafer transport, the two new standards would compare with the semi-standards that exist already for 300 mm wafers and for a FOUP. And once these two new semi-standards are available, one can work on equipment interfaces like EFEMs and load ports, and even on inter-tool transport definitions. The task force activities were started in early 2018 with the preparation of the lamella carrier standard that includes form factor, geometrical dimensions, and material choices, but also the requirements for identification and handling of the lamella carrier. After many constructive meetings, technical exchanges, and several iterations, the first semi-standard for such TEM lamella carrier was accepted and released in November 2019 as SEMI E1770919 document. In 2020, a start was made with the preparation of the lamella carrier container standard. Again, this second new standard will specify the form factor, the geometrical dimensions, and the material properties of a lamellar carrier container, the so-called LCC. But to arrive at the new standard, it will also be required to consider how the lamellar carrier will be transported in and out of the container, and also how lamellar carrier identification within the container will be realized. So the task force members started with a high-level review of what characteristics are relevant for LCC and what kind of specifications need to be included in the new semi-standard. For example, the number of lamellar carrier slots, the type of LCC identification, or even the need for ambient control. It was rapidly realized that what initially seemed a relatively easy exercise in fact is way more difficult. The definition of LCC is complex and includes many relevant details that only can be defined based on clear workflow definitions. And for that, IC manufacturers' inputs are needed. These IC manufacturers' input were successfully obtained via a customer survey that was prepared by the task force but executed through SEMI headquarter in Q4 2020. And luckily, all key top 10 IC manufacturers responded to the survey. Finally, as the devil is in the engineering details, end of 2020, it was decided to create dedicated focus teams in which marketing and engineering experts from the competing microscopy suppliers work together to translate the top-down market requirements into bottom-up engineering solutions. In retrospect, I would like to spend a few words on the challenges that were encountered and how we achieved the desired results. The first challenge was really co-opetition, or how to cooperate between competing companies. I think that meeting task force members in a neutral semi-headquarters setting really helped to foster personal contacts. And also that building mutual trust over the last 3 years was key to get the technical discussions going in the earlier mentioned focus teams. The second challenge is the time it really takes to develop global standards. How do you involve all stakeholders, and how do you quickly get to a consensus despite different interests, different cultures, etc.? Here I think it's important that all stakeholders are convinced that developing the standards is really important to secure future business, and luckily for our task force that happened to be the case. Most task force members were very active and engaged. And the last challenge was the information exchange between the IC manufacturers and the equipment suppliers. While the IC manufacturers have a keen interest in the task force activities, they cannot disclose their internal working methods or strategies in public. But to overcome the confidentiality issues, semi-hosted surveys are very effective. In the end, the IC manufacturers were able to provide relevant inputs through this survey. With this last slide, I would like to conclude this short presentation. In summary, getting many TEM data requires automation, and equipment automation requires a minimum set of standards to ensure industry-wide acceptance. Based on 3 years' experience, I conclude that developing such TEM automation standards within the SEMI Standards organization is effective thanks to SEMI's respected, independent support to our industry as a whole. Our task force has been able to already release a first relevant TEM standard and is on its way to release its second standard in 2022. Thank you very much for your attention.
Hello, I am Wuyts and I will talk about privacy-preserving amalgamated machine learning for semiconductor manufacturing. And I will first explain this context and then talk about standardization. So you know that semiconductor manufacturing is a very complex undertaking. It is complex because the machines involved are very complex and actually consist themselves of many subparts. It's also complex because the whole chain of operations is very complex, and that means that there is at all times a lot of parameters to learn about, to tweak in order to end up for a particular design with, in the end, a wafer of high quality, good yield that is cost effective. So a very complex process. And complex processes lately means, because there is a lot of parameters involved, that you can use various forms of AI to help learn about parameters, set parameters, or on the fly adjust parameters to achieve a desired outcome in each of these steps. That means that this AI can be statistical processing, it can be various forms of deep learning, it can be statistical approaches, other ones like clustering, it can be random forests or tree-based approaches, etc. What they have in common though is that all of these techniques require data. And what we see is that this data is typically limited to a single process step, namely what is available in the machine that this particular AI is optimizing, or in the case of the fab, what data it has available from the pipeline. And as a result, this data remains locked in these silos and is actually not made available to other steps, even though AI in other steps could actually benefit from what is happening in the other parts of the process. Now, I already briefly mentioned it, but one approach, and one that is actually being followed and for which standardization is available, is that subsets of this data are being shared. The problem is these are only subsets, and they can be shared with a fab. They are sometimes shared between particular vendors, for example, for metrology steps that happen after a particular manufacturing step. But it's only limited amounts of data, and as a result, there is also limited benefits for the AI. Now, you don't hear me complaining. This is a very important part. The more data, the better. But question is, can we make even more data available? And what we see is that there starts to be approaches. For example, federated machine learning is one where the AI is collaboratively built. And that would mean that every participating machine will learn a model, a single model, a global model, but only on their data. So the data remains private, but the models are then shared and the models are combined. And by itself, that's a way to not share data, still have models that are trained on a lot of data. The drawback is that it is a single collaboratively built AI model. And in the case of, for example, voice assistants like Siri, that turns out to work pretty well. But in this case, it would mean that you might end up with a collaboratively built AI model that does not quite do what you want to do. And as a machine vendor, you need to be willing to share the model that you trained from your data. So what we are proposing as Imec is something called amalgamated machine learning. And that's another way of approaching this problem by keeping the data private, but also keeping the model private. And that means that in every step, every vendor is again allowed and can use their own machine learning model to predict what they want to predict, but we link the models together and we let them share derived model information. And that derived model information by itself cannot be used to reconstitute the data of that particular step, nor the model of that particular step. But everybody improves their accuracy and they can learn from other steps. This is not new. It is something we developed first in the context of big pharma companies, but we now use the same ideas in semiconductor manufacturing, published a paper about it, and we're actually looking for more partners to help push this technology forward. Now, I promised to talk about standardization, and that's because we believe we need to move beyond data governance. That's important, but we would argue that we also need to start to think about AI model governance. Think about what threat models do we want to protect against. Think about what would be safe derived model information to share. And last but not least, think about standardized privacy tests, a test that can guarantee that partners can safely collaborate, that the data and the models and the information they have inside their machine as a result, the knowledge in building that machine remains private. Last but not least, we want to thank the sponsors of this research, namely the MADEin4 project, which is an ECSEL joint undertaking, and the Flemish government in the Flanders AI program. Thank you.